Today I'm here to talk about the horizontal pod scaler, KEDA, and Kubernetes. So scaling an application on Kubernetes, basically. And specifically, the idea I had was to talk about scaling an event-driven application. And after I wrote this title, I realized, hey, event-driven can mean a lot of things. It's kind of, a loaded term, maybe. So specifically, this is referring to evented I/O, or non-blocking, or asynchronous I/O. Applications that use that paradigm. So with that out of the way, I'll jump straight in. I'm Evan Shortiss. I'm a developer advocate at Red Hat. My background is in consulting, so I have built applications, on top of our platforms at Red Hat. Primarily built mobile, web apps, and back-end applications. A lot of JavaScript in my past, hence the influence that's going to have on this talk. These days I'm living in Los Angeles, but I'm originally from Ireland. And if you're wondering who the real handsome guy in the photo is, that is my dog, Boru. He's a Korean Jindo mix. Also, I figured I'd start off light, maybe with some mild jokes, to lighten the mood. So I don't know if anyone has been to California or has visited, but you see lots of signs like this. But of course, they don't talk about Kubernetes. But hey, yeah, this talk will expose you to Kubernetes, Node.js. So there may be dependency bloat, complexity, and other harm caused by this talk. And also, we have to get a mandatory JavaScript joke in, right? So if you're familiar with JavaScript, maybe this resonates with you, downloading the entire internet every time you, build a JavaScript application. But I can't leave it just at that, so I have to, get a Java joke in there too. So let's not forget log4j. No one goes away unescaped, Java or not. And I think the one thing we can agree on is that regardless of our tech stacks of choice, we all love to work with tech and talk trash. So let's get started and have some fun. So today, like I said, we're going to talk about non-blocking I/O and event loops, specifically in the context of Node.js, but it can apply, I'm assuming, to Vertex as well. It can apply to Java stacks as well. I'm going to talk a little bit about the idea of back pressure for your Kubernetes application. Hey folks, you missed all the good jokes. So I'll talk a little about back pressure and your Kubernetes probes and how that's important before I move on to the other topics, such as auto-scaling and talking about metrics. And after that, so once we've talked about that, I'll cover the horizontal pod autoscaler in Kubernetes. Then I'll talk a little bit about worker threads and how they're useful for event-driven I/O or applications using non-blocking I/O or asynchronous I/O, depending on your preferred terminology. And then finally, I will talk a little bit about scaling using custom metrics with KEDA on Kubernetes. And the reason I'm giving this talk, or what inspired it a little bit for me, is because when I was working in consulting once upon a time, I worked on an application that was basically a mobile app. Typical architecture, right? It has a back end, and then there's some other services behind the scenes. This is obviously quite simplified, but we had this service that was doing a lot of work. So you can see it there. It's labeled as the data service here. And it was talking to message queues. It was writing data to a database, doing tons of serialization and deserialization of XML and JSON payloads. And it was even communicating with Apple's push notification service to send push notifications to a mobile application. So this thing was doing a bunch of work. And one day it exploded. And we quickly found out that the reason it exploded was because Node is single-threaded, and if you give it too much to do, it will fail catastrophically, or it can. And we came up with all sorts of crazy hacks to work around this because we were running this application on a platform that wasn't Kubernetes. It was a platform designed specifically for running Node.js applications, and it was a SaaS, or a backend as a service is what you can think of it as. So it was really useful for us to easily deploy our application. Not so easy to horizontally scale or just scale in general because there was lots of implementation details hidden from us. So we did all sorts of terrible things to get this application working, and you can ask me about those after the session, but we did get it working again on that platform. But today I'm going to analyze how we could do this if it was not 2016, which is when I was working on this, how I would do it today on a modern platform where we have lots of better tools from the CNCF and from the Kubernetes community and just a more modern Node.js version as well. This application was running Node 4, I think. Or actually, no, it was running Node 0.12, I think. So it's pretty old, and it didn't have like all the nice new features we have today. So first things first, before I dive into the demo or anything like that, how many people here are familiar with the concept of non-blocking I/O? I assume a lot of people. Yeah, right. It's not that new. And similarly, if you're familiar with event loops, anyone familiar with that concept as well? Yeah, they kind of go hand in hand a lot of the time. If you're a Java developer, Netty or Vertex are probably familiar to you. If you're like me, you may be using Node.js, for these high throughput, low thread count servers. But it doesn't matter. The topics I talk about today should be relatively transferable. So I'll very quickly just recap. This is a drastic simplification. But if you think of blocking I/O, it looks something like this, right? You have a thread per request. You run some logic. Maybe you do some I/O. The I/O takes up a large chunk of time. And then you return to more logic, right? You're running your imperative code. And this happens for every request. Whereas when we move to non-blocking I/O models, the idea is to take the I/O, put it somewhere else, right? So we're not having a thread per request necessarily. Instead, we have a pool of I/O workers in the case of Node, for example. And what that allows you to do is something a little like this, right? So requests come in. Your main thread that's executing your business logic can be idle when I/O is happening. And there's snapshots of time where it executes logic to actually dispatch I/O operations to disk or to network or process intercommunication, right? So requests come in, your JavaScript or your Java layer handles them, and then if they need to do I/O, it goes down to a thread pool, effectively. And when you're finished with that, you can then terminate the request and move on with whatever else you need to do. In Vertex, this is pretty nice and concise. You can see an example here of a HTTP server. All you do is you call the method to create a HTTP server, you register a callback, any request comes in, goes through that callback. Nice and easy. You're not dealing with any of these specific I/O there. Same with Node, looks the exact same almost, right? Nothing surprising here. I think a more interesting example, just to solidify this, is this basic Node server that allows you to upload, post data to it via HTTP, right? You create a server down here at the bottom, you pass it a callback for every request that comes in, and when that request comes in, we register a handler, and that allows us to capture any inbound data events. So this is a good demonstration, I think, of non-blocking I/O, because this data callback here, that'll only be triggered when there's a buffer available to be passed to your JavaScript code. Until that buffer is ready, your JavaScript can do other things, like run and process other requests. It's not blocked waiting for that buffer to come across the network, right? It just doesn't have to wait. And when that does happen, when data is ready, it'll just call this callback, and you can push it into an in-memory array, whatever you need to do with it. And then when there's no more data coming along on that TCP stream, Node will tell you. It'll figure that out, trigger this end callback, and then you can trigger another function to send a response because you're done dealing with that request, right? So it's kind of a nice model. You're just building lightweight functions in response to events. And that's kind of the crux of what I'm going to talk about today. Navi, if you're a Zelda fan, this is the important part, right? So yeah, as Navi said, listen. So this is where things become problematic as well, right? So this model is really nice, I think at least. I've been doing it for so long to reason about. You just think in small chunks of logic, and you don't have to worry about that I/O. So if one request comes in, it's no big deal, right? It comes in, it gets popped off the event queue, your JavaScript does something, and then passes it back down for more I/O, potentially. No big deal. Now, let's say you're executing some logic that blocks for 50 milliseconds on your main thread. That's really bad. 50 milliseconds is a lot of time. But in this scenario, if it's over 1 second and there's no other requests, you don't care. No big deal. Then it does something else and blocks for 100 milliseconds. Again, no big deal because there's no more requests. Another request comes in to your server. And again, they don't overlap. You don't care. You're fine. A third one comes in. Same thing again. They seem to be fortunately not overlapping with each other in this perfect scenario I've imagined up. But in reality, right, what's happening here is we have 3 requests and they're executing some CPU-bound logic on our main thread. And that might have resulted in almost half a second of blocking, right? So if any other requests try to come in that same time frame, they can't be processed because they'll get stuck in the queue. because our main thread is busy. And this is a real concern in an application that's using non-blocking I/O, right? If you start to block your main thread, you cannot process those requests. So what does this look like? Say we have a request come in here, the green one comes in and it gets popped off the event queue and it starts processing, and for some reason you have a while loop that runs for 500 milliseconds, which is way too long in a single threaded app like this in Node. The other request that's in the queue is stuck waiting for 500 milliseconds. So that's a terrible experience for anyone who's waiting on your server, right? The response times are going to be way up. So that's not ideal. What you really want is something that looks a bit more like this, right? So each request is blocking for a very tiny slice of time. Like it's almost imperceptible. It's so low, that time slice. That's where you want to be. You want each of your callbacks for I/O or whatever in your app to be very, very short and quick. And then you can fit a lot of them into whatever given time frame you need to. So let's take a look at an example here. I have a little demo app here. If you want to scan a QR code, it'll bring you to the application. It's very basic, but it's going to demonstrate my point. If you guys use this application, what I'm going to do is show you how it can become unresponsive pretty quickly with just a small few of people if we have some expensive logic for each incoming request. And then we're going to see how we can scale that up using the horizontal pod autoscaler. So yeah, if you fire that application up, super basic. All it does is allows you to request a cookie. And when you request a cookie, it will tell you how long it took to do that logic on the server. So for example, I've set the bake time for my cookies in this application to be 100 milliseconds. So I'm going to block the server for 100 milliseconds. And then you can see my response time here was 139, which means, I guess, 39 milliseconds of Wi-Fi network latency. So we can block for 5 milliseconds. Those ones come back quickly. And block for 100, and they come back slowly. Now, what would happen if I decided to hit this application with some extra load, right? So if I used a load testing tool like Apache Bench to have 5 concurrent requests, which is incredibly low, and do 1,000 of them, and I go to that endpoint, right, the event loop. I got to get the URL now from my code. So I can go to this blocking endpoint. And when I execute this, and I go back to my browser, what I'm going to see is the app suddenly can't respond too quickly. It's going to take a while. Let me make that higher. 1 second. There we go. So if I start making these blocking requests to the app, right, the response times are going to climb depending on what time you hit the server. You can see they're climbing up by double here, right, after just 5 concurrent requests. And this is a big problem with Node apps or event-driven I/O apps that have a single thread. It's very easy to mistakenly write inefficient code in your callbacks, and therefore they get backlogged. So that's what happened, right? We didn't really follow best practices in this application I wrote. It's getting backlogged because we're executing too much CPU-bound logic, and therefore we're going to see increasing request latencies the busier the app gets. So a good rule of thumb is keep your callbacks lean in Node or in Vertex or whatever evented I/O framework you're using. I like this meme that I found. It's basically like, yeah, if you put while loops or some blocking logic in your Node app, you're going to have a bad time. So you just saw me do that stress test. And what's happening really when you think about it is we're getting this conveyor belt kind of pattern happening where the requests are coming in, but because each one is taking 100 milliseconds to process, the more that come in, eventually they'll backlog up far enough that your app chokes. And yeah, something like this happens, right? Your requests start failing. So how can we handle that for a start? Let me quickly show you. So what I have here in my terminal, if I go to this folder, I'm going to run a quick load test on this application. I've set up a load test scenario already, and I know what's going to happen, but I want to show you guys. So if I run Gatling, is anyone familiar with Gatling, the load testing tool? Yeah. So it basically allows us to define like user behavior, how it might happen in a real world scenario, and test our application to see it can hit our desired user count for different endpoints. So what I'm going to do is I'm going to run this Gatling simulation from a laptop here, or from a droplet I have running in the cloud. I'll go ahead and run it, and I'll call it our baseline simulation. And actually, before I run it, I should just show you. This application is running on Kubernetes. It's running on Red Hat's OpenShift platform, which is based on Kubernetes. I have 3 replicas of this application running. And right now, it is configured correctly. So I'm not letting it use certain features. I'm going to enable some of these features later to show you how we can scale it a little bit better. But yeah, I'll call this test the baseline test. And once it starts up, what's going to happen is this application will come under some load, and we can go ahead and look at some of the metrics from the application if we like, such as memory usage, right? So we can see here in OpenShift, each pod is using about 50 megabytes of memory, which seems totally reasonable. And if we take a look at CPU, it's, oh wait, that's not the CPU graph. There we go. It's suddenly spiked up because I started a load test, right? Because Node generally is pretty efficient with memory because it's not spawning a thread per request, but CPU can get pretty busy, especially in this application I deliberately designed to use lots of CPU. And you can see already that our load test is reporting, lots of requests are getting through, but lots are failing. They're KOing, which means they're failing or they're timing out. So there's something seriously wrong with this application, and what's wrong is it's spinning up a lot of CPU logic per request. The requests are getting backlogged, and they're falling over. And you can see based on this CPU chart, something really went wrong here because there's no CPU time shown for a brief period. And I don't know why that is, but I have a suspicion. And if we come over here and take a look at the events for our pods, we can see that they're actually failing to respond to their probes. So in Kubernetes, we have liveness and readiness probes to check our pods are healthy. They can actually respond to requests, right? And they're in a healthy state. They're basically able to pick up and respond to requests. And what's happening is this app is so overloaded that it can't actually tell Kubernetes, yes, I can accept requests. Because when Kubernetes asks it with this basic endpoint, the app is so overwhelmed, it cannot say, I'm okay. So that's the first thing we need to fix before we can think about scaling it any further. And to do that, what we need to do is handle back pressure, right? So we need to actually protect our application from being overwhelmed. It needs to have some smarts to say, okay, hold on, I'm already dealing with 500 concurrent requests. You need to back off. So this application, as I said, is written using Node. And if we take a look here in this application source code, we're building it using a Node framework known as Fastify. And there's this great plugin for Fastify called Under Pressure. Is that font size okay? Cool. So this plugin is called Under Pressure. And what that allows us to do is detect when our Node app is under pressure, as you might have guessed. And I'll talk more about the types of pressure your application can be under in a moment. But basically, with a Node app, the event loop that's responsible for processing events can be utilized up to a high amount. And also, it can be delayed. So the delay is basically the time between each event it's able to process. And if that delay reaches a certain threshold, this plugin can detect that, and we can automatically start replying with service unavailable responses if we like. So effectively, we're rejecting incoming requests with a 503 to protect our service. Sounds bad, but it's a lot better than the service just completely falling over. It's better to accept what you can, most likely, rather than falling over. So what I'm going to do is I have that plugin disabled right now, but I can edit my deployment here, set the environment variable to enable it. And what we can do now, once that's enabled, is we can start a new load test, and hopefully it goes significantly better. But what you can see from this previous one, just before I start, is tons of requests timed out, right? We had like 30-something% of requests timing out. Lots of them are getting 503s because the load balancer on our cluster is telling it, hey, that app is not even available. It's completely fallen over. So yeah, if I run another load test now that I've applied this under pressure module to our server, I can say, I'm just putting in a note that this is using under pressure enabled. And this load test should be significantly better, right? So if we go into the metrics here in our OpenShift dashboard, And all of this is backed by Prometheus, so you're probably familiar with Prometheus metrics. We can see if we look at the CPU graph this time, right? It takes a second to update. There's usually a bit of a delay, but what we're going to see is the CPU will still be high, but our failures over here will be significantly lower this time. We'll still have failures because we can't accept all the requests, but our server will not completely fall over and choke. So if I open another tab here, and I take a look at our application, and I go to the pods, and I go to the pod events, oh, we are seeing failures. Did I not set the thing right? Let me see. It shouldn't be failing right now. I probably messed up and set something incorrectly. Huh, that's set to true. Okay, no big deal. I'll come back to that in a moment. But I did a load test earlier anyway with that set to true. And what you'll see happens is if we look at the response times for the request and the request success rate, before we are handling back pressure, right, tons of requests are failing because our pods are dying, our application's no longer running. But after we apply back pressure, a smaller portion fail, and lots of them just get high response times. So that's the first step before we scale our application. Now, once we have protected the application, that's when we can start, I think, at least in my opinion, start to scale it using the Kubernetes pod autoscaler. So using the horizontal pod autoscaler, we can add more replicas in response to the demand or load on our application. And the default metrics that you'll find most often talked about with the pod autoscaler are CPU and memory, right? So in the case of this application, if we look at results from a baseline test, you can see that the memory is pretty constant, right? And it's quite low. It's 50 to 60 megabytes per pod. So this application isn't creating a lot of objects in memory, so it doesn't really make sense to scale it by memory. But if we look at the CPU, what we can see is it's not bad either. It's using about 1 core per pod, right? So 1 CPU core per pod in this application is maxed out. So it probably makes sense to scale this out when it's topped out on a CPU core. And the reason we're topping out at exactly almost 1 core per pod is because Node the main event loop can only use 1 core, right? Now, internally, Node does have multiple threads for handling I/O and garbage collection and all that other work it does behind the scenes. But like I said, this app isn't really doing any real work, so the garbage collector isn't too busy. So yeah, memory, pretty safe. We don't need to scale there, but in this application, we should scale based on CPU utilization. So let's see how we can go about that. So back in my editor here, I have some Kubernetes manifests for this application. And if we take a look at this one, it's just a regular Kubernetes deployment. So we are defining our application. We're telling it which image to use to deploy the application, which container image. We have some environment variables set here. You can see I'm telling this application it should request 1 CPU from Kube. So Kubernetes will make sure that it has at least 1 CPU allocated for this application, and it can burst up to 2 CPUs, which might be kind of interesting to see because we just saw the CPU graph there, and it never bursted up above 1, right? And that's because of that single-threaded nature of the Node main event loop. So yeah, by default, I've set the replica count to 3 somewhere here. Yeah, there we go. So you can see the replica count is set to 3. So that's hard-coded. But what we can do is we can use the horizontal pod autoscaler and apply this manifest to our application or to our namespace on Kubernetes. And what I'm saying to Kubernetes is I want this application to scale up more replicas if the average CPU utilization of each pod exceeds 65%. And I want to go up to a max of 10 replicas. So basically just a kind of safety mechanism there to say don't scale beyond 10. So what I can do is go back to my terminal here for this application. I can do a Kubernetes apply, and I can apply this pod autoscaler to my namespace for my application. And now if I take a look here in the UI, we can easily confirm that it's set now to autoscale to more than 3 pods. We can also observe this as well using the CLI. So we can do describe HPA, and we can see that it has been applied to our cluster. And we're currently, at the default min number of replicas, which is 3. So now with this configuration in place, if we do another load test, again, I'll run it straight from this server I have here. And I will say HPA enabled. And what should happen now with this load test is after a little bit of time, this number of pods will auto-scale up to more than 3, basically. I've seen with this particular test I'm doing, usually is around 5 to 6 pods, roughly, give or take, is what it will scale up to. And since this load test can take a couple of minutes, I'll skip ahead and show you some graphs. After this application scales up, the response ranges dramatically drop, right? Because we have extra replicas, so each one is receiving a distributed amount of load, meaning our event loops are less backed up. They're still backed up a little bit, but significantly less so, and we get this much nicer looking result, right? So we're seeing most response times are less than 100 milliseconds, which is it's pretty fantastic. But one thing to be aware of is there is a ramp-up period, right, where that first initial load that comes in will only hit 3 pods, and we have to wait for the horizontal pod autoscaler to look at the historical metrics and say, okay, should I scale, or is this just, a brief spike? And you can tune the pod autoscaler to say, hey, I want you to be more aggressive in terms of checking how frequently, or in terms of how often you should check the metrics, and how far I should look back before scaling up and down. So during that scale-up period, you can see the response times are not so good, but afterwards everything's okay. For example, if we come over here to my terminal, or sorry, to my cluster now, yeah, you can see here auto scale to 5 pods, right? So it has scaled up and it should be behaving much better. Like we can see there was some failures initially, but the failure rate will have gone down now because it's scaled up. Now, one thing to note is that even with that scaled up application, this application has just a basic get endpoint, right? That's the one that loads up that UI you saw, which was this here, right? So this UI, it should load up instantaneously. It's serving up a static index.html, right? There's no actual logic here. So it's kind of still a little disappointing that even with 5 or 6 pods, some of them are seeing a response time of a second for that basic page. And some of the requests are taking almost 200 milliseconds. So things are better, or they're good, but they could be better. And if we look at maybe the reasons why this is happening, nothing looks too unusual if we look at the CPU graphs from that test. CPU utilization, if you average it across all the pods, is probably around 65% or less. But if we look at metrics from Node itself, that's where things get interesting, right? So here you can see on the left the event loop lag before we scale up to 3 pods. It's a disaster, right? You see spikes of up to 3 seconds. So that means if you hit that pod at the right time, your request could have been delayed by 3 seconds because there was a huge spike because of that load. And after it scales up, you see it becomes much more consistent. But it's still, there is a lag there still. So requests can occasionally get backlogged even with 5 pods because we're running CPU-bound logic. And we can also see that by looking at more metrics. So if you expose more metrics from your Node app, you can expose the event loop utilization. So that's basically the average of how busy the main thread is. And even with 5 pods here for this application, the main thread is consistently hitting like 75% utilization because we're running that CPU-bound logic on it. So things are better, but they're not great. And that's where I'm going to quickly talk about worker threads in Node. I think in Quarkus, if you're a Java person, I think they're called worker threads as well, or verticals. I'm not sure what the term is, but the idea of offloading CPU-bound logic from that main thread, right? So Node does have threads. We've learned from Java developers how to actually build real backend applications, I guess. And Matteo Collina, who I follow on Twitter, and if you're interested in Node.js or JavaScript in general, he's a great person to follow. He's a big contributor to Node, and he's developed the Fastify framework. Really, really knowledgeable person in that community. But he talked recently, last week actually, this tweet went up when I was putting together this talk, and I thought it was really interesting. So he talked about the idea of multi-threading and people asking about when to use worker threads in Node. And he says three things, right? He says, use worker threads if your execution is CPU intensive, which in this app that I deliberately designed to be CPU intensive makes sense. Also, if you have multiple cores available or CPUs, again, threads make sense. And in this case, on this Kubernetes cluster, I have a bunch of CPU resources available. And then finally, he's saying, make sure you're aware of the latency overhead, right? So if we're forking some workloads down to a pool of worker threads, there is going to be a little bit of latency for that particular workload. So yeah, I'm going to go ahead and show you this application again quickly. So the endpoint that you guys have been hitting when you request that bake cookies in the app, it basically just runs a function that executes some CPU-bound logic, which, as I said, in Node is not always a good idea. And I have a flag here that enables it to use threads. And if it does use threads, what will happen is, I won't go into the code too much, but basically it'll create this little pool of workers up to half of the CPU threads available, and it'll dispatch the work onto those threads. So I'll go ahead and enable that feature now. So if I go into OpenShift, I can just quickly modify my deployment. And I have this use threads variable here. I'll set it to true. And our application should get redeployed and spin up a bunch of new pods. So if we go back here to my terminal, and I make the font a bit bigger maybe, there we go. You can see now that we had pods spin up, new pods, and they're ready. So I'm running the same application, but what I'm doing is I'm allowing that particular endpoint that's busy to be run in a thread pool in JavaScript, which is kind of nice. So to execute that, I'll just run a load test again, and I'll show you all these load tests at the very end so we can see the differences between them. So yeah, go ahead, run the load test. Locally, I want to run this first one and say with threads. Oh, and one thing I want to do actually before I run this load test is I'll delete the autoscaler. So I'm just going to not autoscale this job anymore just to see how it does with 3 pods with threads, just for the sake of comparison. So I will delete the autoscaler. There we go. And if we come back here, just make sure we're at 3 pods. There we go. So now we're back to the baseline state where we have 3 pods, except this time they can leverage extra threads. And if we go ahead and run that load test, what will happen is there'll be a bit of latency overhead in each pod as it spins up the first set of threads, but after that, things will get a lot better. Now, I'm going to skip ahead and just show you the result quickly that is obtained if you do this. So you can see on the left, when we had those 5 or 6 pods without threads, the app was pretty good. It was doing great. But with 3 pods, with worker threads, it's even better, right? So by using less pods, by just offloading that single endpoint to a thread pool, things look even better, right? So most of our requests now are are less than 150 milliseconds, right? So the response times are way better. So if I scroll down here, you can see with the threads, the max response time now is cut down by almost 70%, right, for this application. And also the 99 percentile is almost cut in half, and the same goes all the way down the board, right? So basically, by just offloading one expensive operation to a thread pool, this application becomes significantly more scalable. We're only using 3 pods now instead of 6, but we're getting better results. So if we were to scale this up using the HPA, it would be even better. But if we take a look at some interesting graphs quickly, the CPU usage with the worker threads is the same as the previous 3 pods, right? So nothing has changed in terms of the CPU usage of this app. It's still using the 3 CPUs. It's just being more intelligent about where it allocates its time. The memory usage, though, is a little higher, right? So threads, as we all know, aren't free. And because we have a pool of threads, the memory usage for 3 pods is about 260 megabytes versus the 180, I think it was, before we were using threads. But I think that's worth paying that little bit extra in memory to get a significantly more responsive app. And then if we look at the utilization of the event loop, if you can remember the graph from before, it was at about 75%. Now it's down at probably an average of 20%, right? So we've taken that really workload that was trashing our server and put it into a tiny little thread pool, and it's much better now. Same goes for spikes. Before we were seeing huge spikes, and they're basically gone, right? The max lag we're seeing now is 70, 80 on average in this particular application. And that's when it's absolutely slammed. So it makes a huge difference. And what I want to talk about very briefly before I move on to KEDA is that what we're seeing now is quite interesting, right? So the CPU is still busy because we're giving it the same amount of work, but the event loop utilization, so that's how busy our main thread in Node is, popping off those events and processing them, is much more free. So this particular application, it has way more headroom to keep growing with these 3 pods in theory before we need to scale it up. But this raises an interesting question as well. Before we use the same amount of CPU, right, the same 3 cores being maxed out to scale our application. But now we would be scaling needlessly because the application is not stressed anymore. It's still using 3 CPUs, but it's not actually that stressed. As we can see from the chart down here, which is showing the event loop being only at 20% capacity or 25% capacity. So how would we intelligently scale this application if it's under load? Because its behavior is different, it's changed. And the way we can do that is by looking at CPU versus event loop utilization. So if you look at the CPU and event loop before we use threads, it grows linearly, right? So that made CPU a really good metric for understanding how busy our application was. But once we started using those threads, CPU stops becoming a meaningful metric for scaling, or it becomes a less meaningful metric for scaling this application, right? Because the CPU usage is growing, but our event loop is not getting much busier. It's because the threads are taking on some of that work. So we should probably scale based on 2 of those metrics now, right? And if you want to learn more about this, by the way, the blog article by Trevor Norris, he's one of the Node core committers, he works for NodeSource, I think, goes into this in more detail, and it's super interesting. He can go way lower into the nitty-gritty of this and talk about the event loop and CPU utilization aspects. And I would also recommend reading Don't Block the Event Loop on the nodejs.org website. So last but not least, now that we have an application that is behaving much better and can be auto-scaled, we may want to scale it using KEDA because we need to use those custom metrics, right? And the horizontal pod autoscaler out of the box, it supports CPU, memory, and a few other metrics. But if we use KEDA, it becomes much easier to support our custom metrics for scaling. And KEDA also comes out of the box with scalers for things like message queues, databases, and other things. But we're going to use our custom metrics. So KEDA stands for Kubernetes Event-Driven Autoscaler. I only learned that recently. I think it's a fun little acronym. So out of the box, it does have scalers built in. I'll be using the Prometheus one today, so I'll be scraping data from Prometheus about my app and how busy the event loop is and scaling based on that. So one thing I found out as well recently, it was started by Red Hat and Microsoft, which is kind of interesting. You can install it using Helm or as an operator using OLM. And the 2 main CRDs we'll look at today, or the main one we'll look at is the scaled object or scaled job CRD. And also at KEDA, you can scale your workload down to 0, which is kind of neat. So yeah, let's take a look at that now. So if I come back to my application, and I look at this folder with all these YAML files, because who doesn't love YAML? You can see here I have some YAML files specific to KEDA here, right? So the first thing I should show you actually before that is in OpenShift here, or in my Kubernetes cluster, I can take a look at what operators I've installed. And you can see I've already installed the custom metrics autoscaler. That is the Red Hat supported version of KEDA, effectively, right? So you can see it provides the standard KEDA APIs. So I can now use those to scale up my application. And if I come over here, I have a KEDA controller I want to define. So this is just setting up a very basic KEDA controller. And what that means is I already have it running, actually. So if I go get KEDA controller -n OpenShift KEDA. So it's already running in this namespace. Yeah, you can see it's already created. I also have an authentication trigger. So with KEDA, to scrape the Prometheus metrics from the OpenShift metric server, I need to have a service account on Kubernetes that can do that. I've already created that ahead of time. So if I do a kget service account, you can see I created one for the metric server in OpenShift. And I've already applied some role bindings as well. So this service account can effectively read the metrics from OpenShift and let KEDA make decisions based on those. What I also have now, and this is where it gets more interesting, is this scaled object. So this scaled object is going to instruct KEDA to monitor certain triggers that I define, and one of those triggers is Prometheus. And I'm telling it the address to the Prometheus metric server, and I'm telling it to monitor the event loop lag for this node app. So basically I'm saying, hey, KEDA, I need you to keep an eye on this metric, and if it goes above a lag of 30 milliseconds, then I need you to scale the application up. I could do the same thing for response time. So for example, if our one of our endpoints is not achieving a response time of say 15 milliseconds, I might want to scale the application up. So let me go ahead and quickly do that now. So I can do a k-apply, Kubernetes apply, k8s / scaled object, and I'll do it based on the say response time for the / endpoint. And if I do another load test, hopefully all goes according to plan, and this application is under enough load that it needs to scale up. So KEDA, and what should happen if I go back to OpenShift now? Hopefully, if this is enough load, this application should auto-scale from those 3 pods, maybe up to 5 or 6 again, based on this particular bursty workload. It may not happen because I left threads enabled. Actually, I should have disabled the threads because it may not spike because I'm using threads. But I think you get the idea. I know we're short on time. But yeah, with KEDA, we can observe custom metrics. So in this case, I'm observing the response times, or as I said, the event loop utilization or the event loop lag if it's spiking. That might be a better metric to use to understand if your application is truly under load in the case of something like Vertex or Node.js. And I guess with that, I'll wrap up. This probably isn't going to scale unless I disable the threads because it's having too much of an easy time right now. So yeah, I'll open the floor to questions now if anyone has any. And thanks for coming. Yeah?
I wonder if you run into a situation when for KEDA scaling you are using not metrics but messaging queue, and you have a non-running transactions, and on the way down when you downscale, how do you manage the situation when the transaction is still running but Kubernetes tries to kill your pod?
Yeah, it's a tough question, I guess. I don't know enough about the scaling to zero aspect of KEDA if you have a long-running transaction. I know, for example, you could set the termination deadline for your pods to be higher, things like that, maybe. Yep. Yeah, I'm not sure. I think you might want to, if it's something that's going to have extremely long-running transactions, maybe it's not a good fit. I'm not actually sure if it's going to be that long that it's a concern to scale down at that point. If no other questions, I guess we'll wrap up. Yep.
The bits you showed for like a Red Hat specific implementation, does that actually require the shift, or is that Kubernetes?
So yeah, that was the Red Hat supported version of the operator, but you don't need to use that at all. You can just use the upstream version on Kubernetes. Yep. It's just on OpenShift. Red Hat has our own supported versions. So we build our own images, and we support those images specifically.
I had a second follow-up.
Yeah, go ahead.
I'm going to take this and then come back to you. So there's Knative serving. I was curious if KEDA also had or is going to have, or similar mechanisms for, it's not the eventing side of Knative, but the serving side. So in other words, I have requests coming in versus just package driven up down. So it could scale to 0 and then invoke, start the system.
Sorry, could you repeat the question?
Knative serving.
Yeah.
Familiar with it?
Yep.
Versus Devnexus.
Mhm.
So I can start I'm curious if I need to use both. KEDA also has a feature which is similar to serving in the sense of
Oh,
scale to 0 and then start your pods based on the request.
I'm not actually sure if it has a feature to do that specifically. I think in that case, you're probably going to want to use Knative serving. Right. Yep. Although, come to our Red Hat booth, Daniel O did a talk about Knative and KEDA, so maybe he can answer that question in very specific detail because he did a talk that may be right up your alley. Yep.
This pod, autoscaler, and KEDA services, are they available on Azure AKS?
On Azure? I actually don't know specifically. If you're running AKS, I believe you can install, the operators. I'd assume so if you have the sufficient permission on the cluster. But I don't know enough about AKS specifically to say yes or no. But if it's Kubernetes and you have kube admin or cluster admin permission, you should be able to install it. I would suspect. Yep. Hey, you're welcome. That's it. Maybe this will scale up this time. I don't know. Of course, I forgot to turn off the flag for the thread, so it may not scale up. But yeah, that's it. If you want to talk more, feel free to come by the booth. We have some awesome t-shirts and swag. And I also have lots of stickers for Quarkus if you're a fan of the Quarkus framework. All right.